Okay. Ready? Which lecture is this? Welcome to E123, Lecture 8. Woo! Good start. Good start. Happy Monday. All right. Is it Monday today? Yeah, it is Monday. It's my favorite day. I start in the morning. I come. I drive to work. I teach 2 hours of ham radio. I go for lunch. I meet with my TAs, and then I meet with you. I mean, it's just a beautiful day. What can a person more, expect? Okay. Today, still FFT. We're going to finish FFT today and then move to spectral analysis. Spectral analysis is one of the most useful things that we can do using digital signal processing. We look at spectrum. It's a great thing. I mean, everywhere you would see this. Even in your, if you have like a plot like this, like, you listen to music, you see this plot, this thing moving, shows you different frequencies and energy in different frequencies. Spectral analysis. You look at, basically, spectrum. Okay, so we're going to talk about this. Again, there's going to be different subtleties in the ability to look at the spectrum. What does it mean when you look at a finite signal, right? Not an infinite signal. Okay, all of these will have some implications, and so we're going to analyze those. Okay, are you ready? Okay, so last time, start FFT, today finish FFT, start frequency analysis with DFT, and then I want you to start reading chapter 10.1 and 10.2. Who started playing with the SDRs? Is it fun? Yeah. It's quite entertaining. Yeah. You can sink a lot of time into this, so be careful. Okay, at least spend time with your families. Okay? If everything else falls apart. Okay, at least that. Okay, quick question, cool things DSP, what is this? Look at this. You want a hint? Who took chemistry? Ever? NMR signal, the first NMR signal of ethanol. 1951. In NMR, different nuclei will emit a different frequency. This is actually a NMR spectrum of hydrogen, but the hydrogen is bound to different type of molecules. So here's H3C, H2C, and then OH. Yes, and then OH. And so it exhibits different frequency that it's going to emit based on how the electrons are pulled by these binds. Anyway, it's really old spectrum. So now, really easy to compute this. It used to be really hard to compute this. Really hard to compute. Now, everything's really easy. Okay, so briefly, we talked about last time. FFT algorithms exploit the structure in the W sub n matrix, right? So the DFT matrix, there's this W sub n to the power of Kn. All these factors, they have a lot of structure. It grows in K in this direction. It grows in N in this direction. It has a very, very interesting structure. We're going to exploit the structure to compute fewer operations. Okay, that's exactly what we're doing. There's a whole class of these type of algorithms that people have developed, again, to exploit structure, to represent things as a series of sparse matrices. For example, this FFT is a very dense matrix, but as you can, the DFT is a very dense matrix, but we can compute it using a certain decomposition, make it super fast. Okay. Well, at least n log n instead of n square. And I showed you how important this log factor compared to the square factor makes a big difference. So all these properties, in particular this one, that if you square W sub n, if you square it, then it's the same as W sub n over 2. Okay? So we had some assumptions. We said we're going to look at decimation in time type of algorithm, and I'll show you what that means. And we're going to assume powers of 2. And if it's not a power of 2, we're going to zero pad to a power of 2. Okay? And then later I'll show you what happens if you don't want a zero pad, what you can actually do. Okay, but we'll start with simple power of 2. Okay, dyadic size sequences. Okay, so what we're going to do is we're going to, basically do some massaging, right? This is just algebra. And the cool thing about it is let's do the equations. Then, okay, so, how do we sort things out? No, simple, and log n. And then change the world. Really, it really made a huge difference in the ability to do DSP. The fact that you can do FFTs is, insane. If you think about how many places, if you just look at how many places link the FFT W library, how many packages do that? Just a huge amount. Okay? All right. Where are we? I lost my train of thoughts. We got it back. We're here. Okay. So what we're going to do is we're going to split. We're going to split the problem into 2. It's too complicated, right? How about we split into 2? I said last time one daughter, one of my daughters, she likes the even ones and one likes the odd ones, and they're each going to compute the sum. Okay, let's do that. Each one is going to do. So we're going to split it into n even and n odd. So didn't do really much. But I'm going to show you that these are actually two DFTs which half the size. Okay, let's see if that actually works. What we did is last time is we defined n to be 2r. So we're going to sum over n, but we're going to change variables and sum over 2r, which basically means that we're going to go over the even sequences. And then in the other one, we're going to switch into 2r plus 1 for the odd ones. Okay? So I just switched n here for the even sequences to be 2r instead of writing just n even. This is the way to write it. And instead of writing n odd, I'm writing 2r plus 1. Okay? That's great. It's beautiful, but really not useful. There's a 2r plus 1 here, which I really don't like. So I'm going to take this 1 times k here, and I'm going to put it, the omega sub n to the power k, and I'm going to put it up here, like over here. So this is exactly what I'm doing. So this stays the same. Now I'm going to have w sub n to the power of k, the sum of this over the odd and this. Okay, that's great. But we're still not there, right? We're still not there because now we have a sequence which is half the size, but still we have w sub n. So we're going to exploit the fact that w to the power of 2rk over n is actually w to the power of rk, w sub n over 2 to the power of rk. Okay? So we're going to exploit this fact. Remember this trick. It will occur very often. Okay, we're going to use it over and over again. Okay? All right, so I'm going to replace these with just, instead of 2 here, I'm going to move the 2 down there. Okay? That's pretty much it. Just move. This is the beauty of algebra. Okay, so now what we got? We got x of k. Now it's a variable of k, right? We're computing a transformation. We're summing over the evens with this. We're summing over the odds with this factor. And then afterwards, we have to multiply with another factor for the odd ones. Okay? So now this is, in fact, a DFT. By definition, this is a DFT of an n over 2 size signal, and we're going to call it G of k. G of k is for the even ones. This is a n over 2 length DFT of the odd sequences. Okay? And we're going to write it over here, but we have this factor that we have to multiply it with. Okay? And this is true for k equals 0 till n minus 1. Okay? So not till n over 2, till n minus 1. Okay? Right? So still we sum over all, n times k. So we end up with different k's. Okay? N different k's. Okay. So now we define this to be the DFT of the even indexes. This is the DFT of the odd indexes, which is great. So let's look at the diagram and show this. I mean, this is beautiful. This is beautiful. Check this out. We're going to take the even. We're going to compute an n over 2 point DFT of these. Okay, great. We're going to take the odd ones, and we're going to compute an n over 2 point DFT of these. Okay. Now all I need to do, in order to compute x of 0, capital X of 0, the DFT at 0, is to take this coefficient and then multiply it with w sub n to the power of 0 and add it to g0. Okay? And I get the result. In order to get x of 1, I take g1 and I add it to h1 multiplied by w sub n to the power of 1. And that's it. It's nice, right? Wait a second. There's way more structure here that we're going to exploit. Okay, so here's what we're going to do. This is still not it. Still too much structure here. Okay? I want to do something even simpler. Okay. Now, let me argue that both g of k and h of k are periodic, and they have a period of n over 2. Now, it kind of makes sense, because they're n over 2 sequences, and you compute a DFT of them. Okay? So if you compute a DFT of this n over 2 sequence, then it has to repeat. If you just continue with the case, they have to repeat. You can actually show that very simply. If you put k plus n over 2, I have 2r. Okay? 2r over here. And w to the power of r, k plus n over 2, n over 2. Okay? So now, from here, I can effectively just, look at this component, which is r times k, and then I have wr times n over 2, which is here, w to the power of r, n over 2. But what is this? Unity, right? This is unity. Basically, you just went over a full circle. Okay, so this is unity, so ignore it. You get this, and then you end up with that. Okay? So they're periodic with a period of n over 2. It kind of makes sense. So both of them they have the same, they're basically repeat. The only difference, actually, is that so they're all the same, right? So for different k's, they'll be the same, except that I need to multiply them with this factor that increases with k. There's another part. Let me just go backwards to here. There's this factor here that depends on k, which is different for k equal n over 2 plus 1. The rest are the same. Okay? So for n over 2 plus 1, this is the same as 0. N over 2 k equals n over 2 plus 1. This is the same as hk 0, except this factor over here is not. Okay, that's why it continues. Okay, so that's different. Okay. So there is periodicity, and that allows you to, improve further. So for the first n of 2 points, we can calculate g of k in this part. Okay, we can calculate this for the first n over 2 points. But the question is how the periodicity of g of k and h of k can still help us to compute the rest, the second half of the coefficients. Well, let's look if there's structure in w sub n to the power of k. If there's structure there, maybe things are going to be nice and sweet. Okay, take a look at this. So for the second part, for the second half, for k bigger than equal than n over 2 till n, the question is, what is that? What? It cannot repeat itself because otherwise then the first half of the whole DFT will be exactly the same as the second half of the DFT. And we know that is not true. Ooh! That's a very positive answer. It is negative. It is negative. If you think about it, you kind of go half a cycle. Right? You can actually derive it. In fact, this is the same as w sub n to the power of k multiplied by w sub n to the power of this, which is actually minus 1. Okay? So it is negative. It is negative. Okay? Okay, so now we can write it this way. The second half is, instead of this being added to, it's just being subtracted to. Okay? So for the first half, you add G and H with those factors, called twiddle factors. And then for the second part, you just subtract it. Okay? So once I compute H and G, I can compute all the x's by the first part adding them, and then the second part subtracting them. Okay? So we previously calculated those, so we just, we're basically done. Okay? So here's the simplification. Okay? What we do now is we take the even, we take the odd, we compute an n over 2 point DFT, we get the result. We multiply the odd ones with these factors. And now for the first part, we just add these to these, one by one. Okay? Take this one plus this one. Take this one plus this one. Okay? For the second part, I take this one and subtract it for this one. Take this one and subtract it from this one. And that's it. Done. Now that's great. So let's see. Our n-point DFT has now been reduced to 2 n over 2 point DFTs plus n over 2 complex multiplication. Okay? So the 8-sample DFT is this. Okay? So one thing that you have to notice is that we really reordered the input such that the output is in order. Okay? We had to reorder that input in order for the output to be in order. Okay? If you think of arrays, maybe you need to do something in order to do that. Okay? So what we're going to do now is we're going to define what's called the butterfly operation, which is one of the most important operations in DSP. And in fact, in DSP processors, right, digital signal processors, like some of the TIs, some of the assembly instruction or the instruction set has these operations embedded in them because it's so important. Okay, multiply and add, and this is a classic one, and also the butterfly operation. Some of them will implement those. Okay, just to be efficient. Today, not so much. Because things are a little bit more efficient. Okay, so now we're going to define this butterfly operation where basically you take g of 0 and add it to this one, and then g of 0 and then subtract it for the other one. Okay, this is a classic. This happens all the time. You'll see this. This is having this graph of plus and minus. It just appears over and over and over. You'll see that the Haar transform in wavelets that we're going to talk about actually does exactly the same thing in the finest scale. We're going to talk about that further. Okay. So now if we actually count the number of operations, unfortunately it's still O of n squared, number of operations. We didn't really solve the problem of complexity. We just broke it into 2 for the first time. Right? But you took 61A, right? Most of you. You know about recursion. If you have a way to compute something by splitting into two smaller pieces, you can take this smaller piece and split it into two smaller pieces, right? And then go in and go forth till you get to the smallest piece possible. And that's exactly what we're going to do. Okay? We're going to take these n over 2 point DFT and we're going to break them into n over 4 point DFTs. Okay? So let's do that. So we're going to take this n over 2 point DFTs. So let's say we look again on the case of n equals 8. Okay? The n over 2 DFT looks like this. Now it's going to look like take x0, x4. So we take the evens of the evens. Okay? We take the evens of the evens, and these are the odds of the evens. Okay? The evens of the evens, and then do an n over 4 point DFT. Okay? And then we take the odds of the evens, and then we do an n over 4. And then we do exactly the same thing. That gives us G0, G1, G2, and G3. Okay? And we had to reorder things accordingly. And then we can get the H's in the same way. Okay? All right? So now what I'm going to do, I'm going to take this and I'm going to break it again. So the n over 4 DFT, we're going to break it again. Okay? So if we break it again, for an 8 sample DFT, n over 4 really is just 2. It's a 2-point DFT. At the end, we're always going to end with a 2-point DFT. Now, what's a 2-point DFT? 2-point DFT is you take two numbers and you add them, and you take two numbers and subtract them. That's a 2-point DFT. You can actually look at the equation, but I mean, it kind of makes sense. What is the DC component of 2 points? You add them. What is the highest frequency? You subtract them. Right? So that's exactly what it is. 2-point DFT is just add two numbers and subtract two numbers. So I take these, I add them, and then I subtract them. Let's put it all together.
What highest frequency subtraction?
What can I all do to get a frequency which is not DC? Between two numbers. Like, what is the low frequency between two numbers? Like, how can I compute a low frequency?
Average DC summation.
So I sum them. That's DC. That's the low frequency. What's the high frequency? Subtract them. Anything I do, I mean, I can either add or subtract. There's really not much I can do with them. I can do it with weights. But the weights here are just 1. Okay? You can actually look at the equation again. I mean, this is actually, what is W sub 2 is E minus J is minus 1. So the factor is really just minus 1. But it kind of makes sense. If you want to do high frequency, high frequencies look as different. It mostly emphasizes differences. Low frequency emphasizes something that changes very smoothly, intuitively. How do I get high frequency? I look at differences. What is, like, to take a derivative, for example. To take a derivative is actually a high-pass filter. Okay? To take an integral, it's a low-pass. Okay? Because you kind of average things. Okay? So you average thing, that's low frequency. You take the differences, that's high frequency. Okay? Does it make sense? It always emphasizes when you take difference. Yes?
So you started out with 2 to the power of n because you want to make sure that you always end up with 2?
Yes. Right. Because I wanted to end up with 2 at the end. Let's put it all together. Look at this. Beautiful. It's really simple. Think of the operations. You take x0 and x4, and you do this butterfly. Add, subtract. Okay, that's it. And then you reach here, right? You add, subtract. That's it. You take x2 and x6, you add, subtract, and then multiply both of them by wn over 2, w sub n over 2. Okay? And then you add here. You take x1 and x5, add, subtract. You take x3 and x7, add, subtract. And then multiply by this factor. Now you're here. Okay? At this point. So now You add, subtract with these, and then you end up with this value. You add, subtract, you end up with this. Add, subtract, multiply maybe by a factor. Add, subtract, multiply by a factor. Add, subtract, multiply by a factor. It's so simple. You just add, subtract, and multiply by some factor. Maybe. Not always. And you do that in stages. Okay? And you do that in stages. And at the end, what you really did is, to compute this value, you went through quite a bit of computation. Like you went through this part of the graph and this part of the graph, right? To compute this value. So it's actually computing more. But you're doing that sequentially. So you're using previous computation in order to compute the next. And this is exactly what we want. We want to reuse stuff. So that's how we make things faster. We reuse stuff that we already computed. Okay? That's how it works. Yes?
Did you add parallelism to make it faster?
You could add parallelism as well. Although the FFT is parallelizable, but because you have to combine and join, it's not as parallelizable as we would like it to be. But it is parallelizable, but it's there's still communication to happen. And there's libraries, for example, for CUDA to do parallelization. FTW does that on multi-core CPUs, and so on and so forth. Yes. Okay, so now let's think. What is the amount of computation in each stage? Is of the order of n. Right? We're doing n operations, the order of n operation in every stage. How many stages? Log n. Because every time we break into 2. Okay? There you go, n log n. Okay? So general log 2 n stages of decimation in time. Each stage is n over 2 complex multiplication. Some of them are trivial. Right? Like just adding, subtracting, very, very simple. Some of them are multiplication with its factors. Okay. Total number is n over 2 log 2 times n. Now, the order of the input must be permuted. So you have to reorder before you do these computations. Okay. So if you want to do things in place, if you want to do computation in place, you have to reorder your array, and then it comes out ordered. Okay? If you're not doing things in place, then you don't have to reorder, but you need to track the indexes. Okay, so the first stage is split into odd and even. What you do is you zero out the low order bits first. So odd and even is just the low order bit, right? The second is to split out the odd and evens of the odds and evens, right? Then that's the second. Effectively, it's just splitting out the second bit. And then the third stage, just a second, is the third bit that you split. And then the next stage is the next bit. And so the ordering really, it's what's called bit reverse order. Every time you flip the orders of these bits. So you end up with a bit reversed. So if this is what the indexes that you started with, these are the binary representation of those bits. If you just reverse the bits, you flip them, then this is actually what the input of the array should be. And you see it actually makes sense. Right? 0, 4, 2, 6. That's exactly what I had in the other side. Yes?
Did you have to reverse units each stage once you add a factor of 10? Like each stage?
What do you mean?
You have to reorder the inputs at each stage?
You have to reorder the inputs first. You do it once. And then you run it through this graph, and then you end up with the right result. Sweet. It's pretty.
What do you mean with decimation in that diagram?
This is called decimation in time. This algorithm is called decimation in time because we always decimated the time into even and odds. Right? We decimated the time component into evens and odds. And then we summed over them. That's why it's called decimation in time. Turns out, and I'm not going to go over this, is that you could also do the same thing in frequency. So instead of breaking the x of n, the small x of n, into evens and odds, you can have another set of twins that, wait a second, I like the output odds, and I like the output evens. And so you can split the outputs into even and odd, and then work from there. If you do this, and it's in the slides, and it's not very, very difficult to follow, but I don't want to go over this too much, because it's exactly the same derivation. You just split the output into even and odd. So you end up that the output evens is a DFT of the first half plus the second half. So you just add the first half of your samples to the second half of your samples in time, and you compute a DFT of that. That gives you the even values. And then the odd values of your DFT is just take the first half of your samples, subtract it from the second half of the samples, now you have a smaller sequence, and you compute a DFT of that. And that gives you the odd. Okay? You can actually work through this and see that. But again, now it's plus and minus. You see this? I mean, the same thing. Plus and minus. You take something, you add. You take something, subtract. And you know what? The graph looks exactly the same. Looks like this. Okay? This is just the summation in time reversed. Where now this one is flipped. And this one is the right way. Okay, so it's exactly the same algorithm, only you do it the opposite way. Okay? You stream this and you multiply plus minus, twiddle factors, twiddle, and then you end up with something that's not in order. Or you can reorder this and then do something like, you just flip the graph, point the arrow the other way, and then it's exactly the same thing. And it makes sense. There is this huge there's a symmetry between the forward and inverse Fourier transform, and right? I mean, it's all the same. So you could do either this way or that way. One of them is called decimation in time. The other one is called decimation in frequency. Questions?
Why is it bits are reversed if you don't do it like that?
So for decimation in time, you do a bit reverse for the input. For decimation in frequency, your output becomes bit reversed.
I know, but why the result is different?
Because you split into even and odd. To split something into even and odd is basically taking all the components which have a bit 0, right? And then combining them together. And take all of those that have a bit 1 and then combining them together. Okay? It comes down to be the same as basically reversing the bits. Okay? Yeah. Decimation in time. Yeah, in practice, decimation in time. What you do is just reorder your array, fire it up, come out with something that's ordered. Yeah. And often in place. Yep.
Do you end up ever optimizing by using both of them? One to go one way, the other to go the other way, so you don't have to move it?
Oh. Well, this is still computing the DFT, so if you compute the inverse DFT, you have to do something about that. Right? This is still computing DFT.
Then you use the other one for the inverse.
You could, yeah, that's a good point. You could do that. It is possible. Yeah, so you don't need to reorder them. So you might save some operations by doing that. There's other tricks that people use, for example, is the fact that if something is real, then it could be symmetric on the other side. So if you start with something real, I mean, you have a certain amount of values, like n real values, right? N real array. But after a DFT, you end up with n complex array. It's double the size, right? But if it's real, then it should end up with with conjugate symmetry. So you really have information that's still n values. So some exploit that too in order to do things in place. You'll see that in libraries that do fast Fourier transform, especially on embedded systems. They'll try to save as much memory and operations like that. Okay, so what if we don't have a power? If we don't have a power of 2, right? So we said, yeah, we can zero pad to the power of 2, but it doesn't give us exactly the DFT we're interested in. It's a zero padded DFT now. It's not exactly the DFT that we want. It might be okay, but what if we have 257 samples or 4,097 samples? Damn it. I have to double now lots of zeros, right? Well, actually, there's something you could do about this. So you don't have to decompose this into actually just power of 2 DFTs. So a similar argument that we did applies to any length of DFT, where the length n is a composite number. Okay? So if you have an n equals 6 DFT, you can do a decimation in time that would compute 3 2-point DFTs and 2 3-point DFTs. Okay? So, or the opposite. You can kind of flip them as well. Right? So there's different options that you could do. Okay? Now what people have come up with is good component DFT, the kind of the basic ones. For example, a 2-point DFT is a really good one. But a 4-point DFT is also a good one, and I'll show you why. But good ones are available up to 20 or so. And many of them exploit different structure for that particular length. So if you look at a 4-point DFT, if we have a twiddle factor of W sub n to n over 4, turns out that this is minus j. Okay? This is minus j. If you have that factor multiplies your signal, you don't need even to compute anything. You just replace the real with the imaginary one. That's what j means. Okay, minus j means. Okay, you just flip the real with the imaginary. So there's not even a computation that you have to do there. You just move data around. This is called radix 4 type FFT. So anything that is a power of 4, you can compute faster because the n factor is just like flipping the real and imaginary components instead of doing plus and minuses, which is pretty cool, right? So composite FFTs can be very efficient. So for example, if I have an n equals 693, it factors to 7, 9, and 11. Okay? And so all of these have DFTs that people have developed. And so you can basically break this into either 9, 11 DFTs of length 7, or 7, 11 DFTs of length 9, and so on and so forth. Okay, so you can break this into a different type of DFTs. Now, historically, people thought that power of 2 FFTs were just faster. And the reason was just an implementation. People just implemented very efficiently. Somebody really sat on the computer, realized how the cache works, and implemented all this stuff and made sure that it works. Okay. And for non-power of 2, they just zero pad. But I would say recently, in about maybe 10, 15 years ago, this changed. And there was this free package called FFT, which implemented different FFT algorithms for almost any length. Okay? MATLAB actually, and even NumPy, uses FFTW. Okay, so in it. It's a, I think it has an MIT license. No, wait. Has a GPL license. But they also give, or a GPL, LGPL license, so you can actually link to closed source. But they also, if you want to use it for commercial use, then you have to actually buy it from them. Okay, so MATLAB does pay them quite a bit. But as it turns out then, that powers of 2 of FFT is not necessarily the fastest one. So this is example on FFT computation on a MacBook Pro that's about 3 years old. 4 years old. And then you look at the time in milliseconds to compute versus n, and that's averaged over many, many instances. Okay, so I just in order to get, because everything is stochastic when you run it on a computer. Okay, so I average over many, many instances. And so you see there's a nice trend of n log n increase, which is nice. And you see that there's really bad numbers, often corresponding to prime numbers that cannot be decomposed very well. Okay? And there's some really nice ones. And the nice ones are not necessarily power 2. So for example, if I had a 224, right, going and zero padding to 256 would have taken longer than, or 192, right? I would have zero padded there. But no, I can actually do a different decomposition from 182, and I can do it much faster. Okay? So that's kind of nice. The ability to do these decompositions and do it very fast. So what now FFT packages do, and there's many of them. Okay, FFTW is one that's free for non-commercial use, and a lot of people use that one. But there's also other packages like that. What they do is, they operate in different modes, but one of the modes is basically, I don't know which one is going to be the fastest. So I'm just going to try all of them. Okay, and I'm going to train for different sizes. I'm going to just run and run and run. And then check, for this particular system, which one is the fastest. Store this in a file. And then the next time I'm going to compute a DFT of that particular size, I'm going to pull in this decomposition, and I'm going to compute this. And this is the fastest Fourier transform in the West. Pretty much. Then they have another mode, which is more kind of like ad hoc a little bit, where they have a good prediction of what they think would be the performance. So if you don't want to run through all this exhaustive training, then you can use this heuristic. Okay, so they have different modes that these things are applied. And when you use a certain size of DFT, it will store this particular size for the next time. Okay, so this has been really, really useful and really has changed the way people think about computing FFTs. And so lots of software will link into the FFTW. Questions? Yeah, you decompose it into different factors that you can have fast FFTs of. Oh, I mean, like you don't necessarily have to decompose it into the primes, right? So, I mean, you can decompose it into DFTs that like anything between 2 to 20, right? So it's not too bad, actually, to do that. You just need to factor, into 2. You just divide by 2, 3, 4, 5, up to 20. Right? So it's not a big deal.
You had a slide for 6 point or that point DFT non-power of 2, and you break it into 3 branches. How
Yes.
do you do that?
Well, you have to, basically you have all these options that you could do that too. And one of the homework questions actually do that in the book is kind of do a decomposition. I think we did remove it. Yeah, I think I'll check whether we have that question in the homework, but it basically is decomposing into kind of a 3-point DFT or something. In the same way that we decompose it into 2 parts, you can actually decompose it into 3. Okay? You break the sequence into 3, and then work from that.
That's how the math works. Because whatever you did was power of 2.
Yes.
3 is different. You should do.
No, so you look at, basically it's triadic numbers, right? So this was dyadic numbers, now it's triadic. So you just think of, 0, 1, 2. That's 3 numbers, and then 2, 3, 4, 5, and so on and so forth. So 0 would work with 3. So you take 0, 3, 7, right? 0, 3, 6, 9, and so on and so forth. That is one group, and then 1, 4, 10, and so on. That will be a second group, and then 2, 5, 8, 5, 11. That will be the third group, and then you basically work out in the same, very similar way. So you decompose that into these. You basically break the input into these 3 groups, and then you work out from there, and then you break again and again and again. Yep.
How does the butterfly function work with a triadic?
No, it's no butterfly then, right? And that's what I said when we talk about the radix 4. When you do a 4-point DFT, you can actually see what happens there. There's this basically multiplying with, W, like basically with a J that makes you flip things. So the end needs to be optimized, and then you explore different structures over there. Okay, I want to go. So I'm not going to go to spectral analysis today, and that basically puts us back into the framework of the same lectures that I had before, because now it's always half a lecture, but we're one lecture behind, which is okay. So if we think about it as a matrix operation, this is also nice to see how does that fit. If you have FFT as a matrix, this is a full matrix. Okay? But what the FFT algorithm does is decompose W sub n into sparse matrices. Okay? So you can decompose that into a even and odd permutation matrix, followed by the twiddle factors, followed by this, which basically breaks into this is add and subtract. You take half. This is diagonal, and this is diagonal. Okay, so you just break it into this form, and so for the case of n equal 4, this will be the permutation matrix. Multiplied by this matrix, multiplied by this matrix. And so each one of them is sparse. And so that's where you save the computation. And you compute it one after the other. And this is basically the idea in this decomposition, okay, is making it sparse. Talking about sparse, what if I know something about my signal? What if I know that there couldn't be more than K frequencies in my signal? Can that maybe help me compute faster DFTs? And so there's the answer is yes, Ben. So there's a recent body of work, started with Anna Gilbert. There's work from Michigan. There's work from MIT. There's actually work from Berkeley. Kanan Ramchandran is also working on this problem. What happens if I have very few number of frequencies that I want to compute? Can I then save computation? And in that case, yes. As it turns out, that in the case where your signal xn is k-sparse, where it has a k-sparse frequency, then you can compute in the order of O of k log n as opposed to n log n. So if out of k number of frequencies, you have, n number of frequencies, you only have k that are non-zero, then you can compute the FFT with the order of k log n as opposed to n log n. Now if k is 3 and n is a billion, and it could be, right? Like when you compute like spectrum of, I don't know, like sky or something. No, I'm serious. Like there's very sparse spectrum, especially if you're looking at a chemical spectrum, optical spectrum. There's a lot of type of spectrum that could be very, very sparse. Then that actually makes a big deal. Okay? So you're welcome to look at the reference for these papers. They exploit the fact something about the signal, which we didn't exploit before. Before, you just took anything, computed DFT. Now, if we assume something about the signal, then it works. As it turns out, for these cases where actually the sparsity k reaches n, then there's no really gain in computation. Okay. All right. We're done for today. I'll see you on Wednesday. Ham lecture tomorrow evening. Ham lecture, 6:30. 6:30 ham lecture. 521 Corey, same place. Yep.